All right, so let's get started. We're going to finish out actually this equilibrium chapter and then introduce our next chapter as well on acids and bases. All right, but we're going to start out with a little bit of review. I'm going to give you this chemical equation here. You're going to balance it and then give me the Kp expression. And then I'm going to set these initial conditions here. And from that, you're going to be able to build me this ice table. All right, cool. So remember Kp, products over reactants. Since this is Kp, we're going to define it in terms of pressure of our product divided by the pressure of our reactant. All right, and then lastly, those coefficients are going to become exponents in my equilibrium expression. Okay. Then we're going to set up our ice table here. We got all of our pressures of our products and our reactants. That I box, that first row, are the initial conditions here. That's that 2.5 atm of the chlorine and the 1.6 atm of nitrogen. I don't have any of my product yet. All right, I'm going to give you a minute, if you haven't already, to take care of that change box. Well, how do we fill in our change box? That's the pretty important one here. All right, so that change box we leave as that variable x. Okay, but then we got to do two more things. We got to worry about the sign of x. For our two reactants, we're going to put a negative sign in that change box. Our products will have a positive sign. And then those stoichiometric coefficients are also going to appear. So for my pressure of chlorine, the change will be minus 3x. Pressure of nitrogen, the change will be minus x. And then for my product, plus 2x. All right, so then to get my equilibrium box here, we're just going to sum up these first two rows. So 2.5 minus 3x. 1.6 minus x, and then just 2x. All right, so we can set up our ice table based just on the initial conditions. Okay, but then how do we solve this ice table? How are we going to figure out what that change variable is? We had a few different ways that we could go about that depending on what we're given. All right, if what we're given is the value of that equilibrium constant, then what we're going to do is go and plug everything back in to our equilibrium expression. So for my pressure of chlorine in my equilibrium expression, I'm going to plug in pressure of chlorine, that equilibrium box. My pressure of my nitrogen, I'm going to plug that in, pressure of nitrogen, into my equilibrium expression. Okay, and then that pressure of that product, that 2x is going to get plugged back in as well. All right, so then what we get is this big algebraic expression. Okay, 2.5 minus 3x. I'm going to make sure to cube that. And then I have my, what was it? 1.6 minus x. All right, and again, just to kind of copy and paste so we can hammer this home here. Where did this algebraic expression come from? I took my Kp expression and I plugged in my equilibrium box from my ice table. All right, and again, in our problem, we can even go ahead and say that we know this is equal to 142. All right. So previously we had some like algebraic techniques that we could have used to solve this problem here. Let's just face it, none of us are good enough at algebra to solve for x right now, okay? That thing is buried in there real deep. It would be really impossible. You have just this very high order polynomial. So how the heck can we go about solving this here? All right, so what we're going to learn how to do is use the magic of our calculators. If you need to borrow one, please do. I'm going to show you how to use this TI-36 Pro. This is the one that's set for the course. Again, these are the ones that we also have to loan. There was a weird one I saw in there. I missed this one. Okay, pretty much any scientific calculator can accomplish this as well, but it might be like a different label of buttons or whatever. So I'm going to show you how to use this one. Okay. Cool. All right, so starting out from our home screen here, what we're going to do is we're going to use this button right here, this num solve. Let's see if we can. Okay, the one above sign, so we're going to have to hit second and then that num solve. All right, again, most calculators have some sort of a solver, but it's a little probably a different sequence for each one. Okay, so now we just have to plug in our algebraic expression that we got from our filling in those components of our ice table here. We have 142. Okay, this is equal to 2 times, and then when we put in our variable, we need to use this button down here, this kind of fancy italicized X. All right, that was all squared. We're going to now divide by, and since we have those two different terms there, we're going to put them in parentheses, both of them. So we're going to put parentheses in to keep them in the denominator and an extra set to keep them separate. So 2.5 minus 3 times that x value. Again, using that fancy x button. This is cubed. So then we're going to multiply that by 1.6 minus fancy x, and then close our parentheses. Okay, so let me just go back and kind of scroll through here slowly so we can make sure we have it entered correctly. I have 142 on one side of my equals sign equals that numerator 2x squared. And then when I'm going to divide, I need to keep both those terms in the denominator. So I got two sets of parentheses. One will keep them both in the denominator. The other one is for my individual terms. So 2.5 minus 3x cubed. And then times my other one, 1.6 minus x. All right. So once we get it all entered in here, we're going to hit enter, and it's going to take us to this next page here. All right. So this is now saying that you have to set a value for x before you can move on to the solve portion. So why is that? All right. Importantly, your calculator also does not know how to do algebra. So instead, it's like, I'm a big computer. You know what I'm going to do? I'm just going to guess and check. I'm going to plug in a number, see if it works. Plug in another number, see if it works. Plug in another one, see if it works. And it does this just hundreds of thousands of times until it gets to the right answer. So you need to tell it about where to look, because there's number line's pretty big, right? So what you're doing is you're giving it what's called a seed value, where you're saying, look around this number here for the solution. Okay? So that means we have to have kind of at least a little bit of a guess. All right, so how are we supposed to do that? Well, let's go back to our problem here. We had talked about ways that we could make sure that our ICE table was correct and that our answer that we got at the end was correct, because there's no such thing as a negative pressure or a negative concentration. So whatever my value for x is here, I can't plug in such a large value that it's going to turn this into a negative number. All right, so we do have kind of a ballpark of what x should be, right? At the very minimum, x is going to be 0. No reaction has occurred, right? At the maximum, that's going to be set by this. So I guess let's look at this red box here. What could the maximum of x be according to this red box? 1.6, right? Beyond that, it's going to make that number negative, okay? If we go over here and we solve for what x would be, right? If this was equal to 0, we would get something closer to around like 0.8, okay? So that's my max value for x. So that's what we're going to seed it at. All right, going back to our calculator. All right. We're going to say, look around that 0.8 value. Our Ka, or our Kp rather, was a nice large number. We know that x is going to be pretty big. This reaction favors the products. So let's set it at 0.8. And then you're going to hit solve, and then you're going to wait patiently, because again, what your calculator is doing is just guessing and checking a ton of different numbers until it can find the right answer. All right. Now, this works for problems like what we just saw, what we can't do algebraically, as well as the ones that we learned how to do that were kind of an algebraic pain in the butt. So if you would rather learn how your calculator works than do all that pencil and paper math, go for it. All right. But the bottom line here is this will also work for ones that we just can't possibly solve as well. Okay. So we get now our value that we've gotten. It says, all right, well, x was not quite 0.8, but close. That value of 0.745, 462, et cetera, et cetera. All right, so going back here, we didn't even do any math. We used that num solver, and we found that value of x equals, we're just going to copy down a bunch of digits here. 0.4745, 462. All right. And then I'm done. All right, so good instincts. Anytime I ask it, probably not, right? Anyways, if we go back, what question was actually being asked of us is what is the pressure of that nitrogen trichloride at equilibrium? And so according to my ICE table, my pressure of my product nitrogen trichloride at equilibrium is 2x. All right, so we're just going to arbitrarily say 2 sig figs here are 0.149, rather 1.49. All right, and what should our units be? ATM. Cool. All right. So in that case, that worked out really well. We just used our calculator. It gave us the value for x. Done and done. We didn't actually have to do any algebra. We just punched in this equation as it is. Okay. Let's try to do another one. We're going to see if we can't break our calculator and then troubleshoot here. Okay. So first of all, I want you guys to try to solve this as best you can, going all the way into the into your calculator. All right, we have our balanced chemical equation of hydrogen gas combining with oxygen gas to make water. We have our initial conditions, 4.65 molar hydrogen and 2.19 molar oxygen. We need to build our ICE table, and then we can use our Kc expression because that value of Kc is given to us. All right, so I'm going to give you all a few minutes, and then let's see if we can do it. All right, so I filled in my ice table. I took those equilibrium boxes and put them back into my equilibrium expression. I can update. I know the value of that equilibrium constant is 12.6. All right, so everybody can check, make sure we got the same expression here. What's up? Yeah. Cool. So that works. I mean, you're kind of just going from the other direction. So, yeah, that could work as well. All right, so let's make sure we're going to punch this in correctly here. All right, so I have my C value, my 12.6. I'm going to set that equal to my 2 times x squared divided by, and then in parentheses, again, I'm going to need 2 sets of parentheses. Right, 4.65 minus 2 times x squared, and then multiplied by my 2.19 minus x. Okay, so now we're going to get to that seed value. Then again, let's pick a big number here, something that could be almost the max that it could possibly be. All right, just to prove a point, because this can happen. So I'm going to press solve. What we're going to see is that it's going to take forever. All right. Again, that's because all it's doing is going in there and guessing and checking around that initial seed value that we gave it. And it's basically like, I cannot find this freaking answer anywhere. I've checked everything. Nothing seems to be working for me. So I'm going to just throw you this error that says, I don't know. I don't know where it is. All right. And then what we're going to do is we're going to go in and we're just going to change that seed value a little bit to see if we can't get a little bit closer to what the actual answer is. So this is one common problem that you'll get. You'll either get a no sign change error, or it could also throw you back a value of x that is just too big, feasibly way too large, right? If it returned a value of x of 40, it's like, okay, well, that's definitely not what my value of x is. All right, what was your question?
I was just going to ask, after class or during break, can we come to you with our different calculators and try and...
Yeah, I mean, we're going to have to Google it. I don't know it off the top of my head either. Like, we may be able to fumble around and find it, but yes, definitely we could see me and we can try to mess with it. Okay, and then, so what we're going to do is just go back and we're going to adjust it. So you can even go like all the way to 0. Let's see. It would really depend on what your actual correct answer is. I typically just kind of start lowering it down a little bit. All right, 2.3 was a little high. Let's just go 2. See what happens. Okay. It will also kind of depend on your equilibrium constant, right? If you have a very large equilibrium constant, that's a reaction that favors the products. So you're going to get a larger value for x. If you have a very small equilibrium constant, then you're going to get a value closer to 0, right? So it also depends on what exactly that equilibrium constant is. But so here, once we gave it that new seed value, now it was able to locate that correct answer. Okay. So a nice feature of your calculator to have it do the hard work for you, to have it do the solver for you. Again, it's not exactly foolproof. Every once in a while, you got to troubleshoot it by feeding it new values. But nonetheless, this can be a nice tool to have since we have these fancy calculators here. All right, so then just to finish our problem, all right, we got that value of x equal to 1.67127. Okay. If we go up and read our problem, it's asking us for the concentration of water at equilibrium. That should be that 2x box. So our concentration of our water vapor is going to be 2x, or whatever that is. 3.34. Now I'm in concentration, so my unit should be molar. Cool. All right, so for our solver here, we can use this numSolve feature of our TI-36X Pros. All right. Importantly, you're going to enter in your equation. You're going to need to make sure to use that fancy X button as your variable. All right, and your sort of goal is you got to give it something to look at, something to look around. So you need to pick a seed value. Ideally, that's close to your answer. The closer it is, the quicker the calculator will be. All right, if you get an error or any sort of an unreasonable value, you're going to just need to pick a new seed value, right? Typically just go lower or higher depending on where you started. Just keep within that range of possibilities. X can be a minimum of 0, and a maximum of whatever is going to make sure that no number is negative on that ICE table. Okay, so last time we also talked about Le Chatelier's principle, the idea that if a reaction is at equilibrium and we sort of disturb it, it's going to shift either forward or in the reverse direction in order to return back to equilibrium. All right, we got a little bit more to add to this, but let's just review here. We're going to take that same gaseous equation that we were looking at previously. All right, and I want y'all to take a second and tell me which direction the reaction is going to shift in if we do the following perturbations here. Increase the concentration of nitrogen. Okay, so this thing is at equilibrium. Everybody's all happy. Concentration of reactants and products is no longer changing. But then I'm going to go in and add a whole bunch of nitrogen to it, throwing it out of equilibrium. How is the system going to have to respond in order to get back to equilibrium? Go in the forward direction or go in the reverse direction? Forward. So now I have too many reactants, and so it's going to move in that forward direction. Okay, and if instead I went in and I added a whole bunch of extra product at equilibrium, what effect would that have? Now we go in the other direction. Now I got too many products, so it's got to shift in the reverse direction. Okay, cool. So that is definitely true. Nothing, I didn't lie to you last time, okay? It turns out that also, though, there's just an overall effect that pressure in general has on these gaseous reactions. So what we're going to do is we're going to take our reaction. Let me copy my chemical equation here. All All right, so we're going to carry this reaction out in kind of this fancy little container here where I have my vessel equipped with this movable piston. Whoops. All right, and what I have pictured here is my reactants in red and my products in green. And this reaction is currently at equilibrium here in this sealed vessel. Okay, but again, it's got this fancy little top on it, this movable piston. All right, what is going to happen to the pressure if I move my piston down? It will increase that pressure. All right, and what about when I move my piston up? What effect will that have? The opposite, that will decrease pressure. Okay. So it turns out that this effect, increasing or decreasing pressure, can actually have effect on our equilibrium here. All right, so let's imagine that we're going to move our piston down. So we're going to increase the pressure of our system. All right, so this will have an effect on shifting our equilibrium as well. In order to see which direction our equilibrium is going to be shifted, we want to make a note that in this reaction here, how many moles of gas are being consumed? 4, right? So I have 3 moles of chlorine gas and 1 mole of nitrogen for a total of 4 moles of gas. Okay. As well as if I look on my products side, how many moles of gas do we have? Just those 2. All right. Well, if I increase pressure by increasing or by moving that piston down, this system is going to respond to relieve some of that pressure by shifting this equilibrium from the side with more gas molecules to the side with fewer gas molecules, right? So my increase in pressure is going to be met with this response. So the system responds by shifting that equilibrium from the side of more to fewer gas molecules. Okay, because this will have the effect of decreasing the pressure, or let's say relieving some of that pressure. Okay, well, if we take this same system and then we imagine we're going to do the exact opposite. We're going to now move this piston up. again, we said that that would have the effect of decreasing pressure. All right, so in this case, if we decrease pressure, which direction do we think our reaction is going to go? Now it's going to go the other direction. So now our system will respond by shifting that equilibrium from the side with fewer to the side with more gas molecules. All right, so for gaseous reactions, and specifically gaseous reactions where there's an imbalance in the number of moles of gas on one side of the reaction compared to the other, we have this effect of increasing or decreasing the overall pressure of the system. If we increase pressure, it's going to respond by shifting the equilibrium from the side with more to the side with fewer gas molecules. And if we do the exact opposite, if we decrease the pressure, now it's going to shift the equilibrium from the side of fewer to the side of more gas molecules. Okay? All right, so this is this overall effect of pressure on specifically our gaseous reactions. We're going to keep with this same sample reaction, and I'm going to tell you that this is an exothermic reaction. All right, and we're going to explore the effect of temperature on Le Chatelier's principle. All right, so first of all, by exothermic, what do I mean? This reaction absorbs heat or releases heat? Releases heat. All right, so what we're going to do is we're going to think about a reaction that releases heat as heat being a product of that reaction. So I'm going to take my chemical equation here, and I'm going to add another product, which is that heat that's being released. Okay, well then let's think. We're talking about the effect of temperature on this system, on this direction of equilibrium here. If we increase the temperature, that's like we're adding a whole bunch of product into this reaction mixture. So which direction is our equilibrium going to be shifted? In the reverse direction, right? So if we add product, that will shift this in the reverse direction. Okay, and then what about if we decrease temperature? That would have the effect of removing that heat from that product side as it was being formed. And this is going to have the effect of shifting this reaction in the forward direction. Okay, So temperature, we also has this Le Chatelier's-esque effect here. It's going to depend on whether our reaction is exothermic, meaning that it releases heat. If we do have an exothermic reaction, we're going to imagine heat as a product of that reaction, right? And then we can think about what happens when we increase temperature or add heat, or decrease temperature and remove that heat, what effect that's going to have on the equilibrium of that reaction. All right? So I want you guys, let's see if we can't work through this on our own. Our second reaction that we were looking at is an endothermic reaction. By endothermic reaction, I mean it absorbs heat. Okay, so a reaction that absorbs heat, it consumes that heat. So what we're going to do is we're going to imagine heat is a reactant. All right, so let's see if we can't work ourselves through these same few changes here. Everybody take a second and see if you can't predict what would happen if we increased or decreased temperature of this endothermic reaction. Yeah, that thing's working overtime or something. I don't know what's up. Yeah, it's pretty warm. I can feel it coming directly from that box too. So, all right. So if we increase temperature, that's like we're adding one of our reactants here. So that will have the effect of shifting this in the forward direction. Okay. If we decrease temperature on an endothermic reaction, then all of a sudden we're decreasing one of our reactants. So that will have the effect of shifting this in the reverse direction. Yeah, great. Unfortunately, I don't have control. We'll take a look, though. Okay, so we have our temperature effect on Le Chatelier's principle here. It's going to depend, though, on whether we're talking about an endothermic reaction or an exothermic reaction, okay? An exothermic reaction that releases heat, so we imagine heat is one of our products, all right? But an endothermic reaction is a reaction that absorbs heat. We imagine heat as one of our reactants here, okay? So first of all, just like before, how would you know whether you have an endothermic or exothermic reaction? Well, I had to tell you, right? So at this point, trust me, we're going to get a little bit further and talk about thermodynamics, and we're going to be able to predict these values of exothermic or endothermic for ourselves. For right now, you would be given that information about your reaction and asked again what the effective temperature would be. Cool. All right. So that is going to cover it for equilibrium here. Although this stuff is going to come up kind of over and over and over again. We're going to see these ice tables a lot throughout the course, including our next chapter, which I'm going to introduce right now. All right, chapter 14, our next chapter is on acid-base reactions. Okay. Acid-base reactions are something that you covered in Chem 1A. We're gonna talk about it here again in this course. You're gonna go into organic chemistry. It's gonna be one of the first chapters you discuss there as well. It's a really important class of reactions that kind of comes up over and over and over again in many different branches of chemistry. All right, so we're gonna kind of expand upon what we learned last semester. Specifically, what we learned last semester was that these would fall into that category of double displacement acid base. Right? When you were learning about different types of chemical reactions, this was one of those class of reactions. Okay, so just an example would be if we took hydrochloric acid and sodium hydroxide. So in these double displacement reactions, what we did was we swapped our cations. So I'm going to move the hydrogen over with the OH and the Na with the Cl, right? They're going to swap places when we do our product side. So NaCl, aqueous, plus HOH, which is a comically ridiculous way of writing the formula for what molecule? Water. Okay. Cool. So, what's up? It doesn't. The order doesn't matter. Yeah. Just like I could have switched NaOH and HCl, NaC, like products and reactants, the order that you put them in does not matter. All right, so it's not that we were lying to you, okay? This is certainly a reaction that happens, but it's kind of just a very narrow view of acid-base chemistry. This is what's called the Arrhenius definition. Yep, same dude. All right, and an Arrhenius acid is one that contains H+, and an Arrhenius base contains OH-, those hydroxide ions. All right, but this Arrhenius definition is outdated. We're going to expand upon that definition. Actually, he's pretty right on about the acids. It's the bases that this is just a very narrow class of bases. Okay? There are way more bases than just hydroxides out there. All right, so what we're going to do is we're going to upgrade to this new definition, what's called the Bronsted-Lowry definition. All right, and in this Bronsted-Lowry definition, an acid is any compound that donates a hydrogen ion. So we call acids hydrogen ion donors. And then a base is just anything that's accepting that hydrogen ion or a hydrogen ion acceptor. All right, so acids are donors, bases are acceptors. All right, and these are hydrogen ions, but we don't call them hydrogen ions. We kind of have like this slang term for them. All right, because let's think about it. Hydrogen's that very teeny tiniest element on our periodic table. It's just got one proton. Okay, so if I'm holding a neutral hydrogen atom in my hand, how many electrons does it have? One. All right, and then I'm going to go in there and I'm going to remove that electron to make this hydrogen ion. What am I left with? Just a proton. All right, so hydrogen ions, we don't call them hydrogen ions, we call them protons. So an acid is a proton donor and a base is a proton acceptor. All right, so then let's look at an acid-base reaction that doesn't follow our old definition. Okay, we're going to take HNO3, which is nitric acid, and mix that with ammonia, NH3. All right, and kind of our big update in our thinking here is an acid and a base. It doesn't describe a molecule. It describes the role that they play in a chemical reaction. Okay, so in this chemical reaction, the role of the acid is going to be played by nitric acid, and the role of the base is going to be played by ammonia. All right, so then when we do our reaction, when we draw our products here, all right, I'm going to look at my acid. That acid needs to donate, aka get rid of, a hydrogen, right? So when I draw my formula here for my product, I'm not going to have that hydrogen on there. It's just going to be NO3. Okay, not only did it get rid of a hydrogen, but it didn't get rid of a neutral hydrogen atom. It got rid of a hydrogen ion, which means that it's left with this negative charge. All right, if I'm going to draw the formula here for my other product, I'm going to look at my base. My base is the proton acceptor. So now it has to increase in number of hydrogens. Over here on the left-hand side, it only had 3. When I draw my products, it's going to have 4 hydrogens. Right, and then likewise, not only did it accept a hydrogen, it didn't accept a neutral hydrogen atom, but accepted that positively charged hydrogen ion. So I'm going to be left with a positive charge. All right, we got some fancy terminology here. Our acid is going to become what we call the conjugate base. Whereas the base is going to become what we call the conjugate acid. All right, and this seems kind of backwards here, right? My acid becomes a conjugate base, and my base becomes a conjugate acid. Well, where does that terminology come from? All right, well, remember, we're updating our way of looking at chemical reactions compared to Chem 1A. We're not going to just look at them going in that forward direction, but we're also going to look at them going in the reverse direction. Okay, if we look in the reverse direction, what is playing the role of the proton donor? It would be that conjugate acid. If we look in the reverse direction, what's playing the role of the proton acceptor? It would be that conjugate base, right? So that's where that terminology comes from. Our acid becomes our conjugate base, and our base becomes our conjugate acid, because in the reverse direction, your conjugate acid is your acid, and your conjugate base is your base. All right, so step one is predicting these products here of our chemical reactions. So let's kind of take note of what we did here. In order to get our conjugate base, we looked at our acid and we decreased the number of hydrogens by 1. All right, not only did we decrease the number of hydrogens, what else did we have to update? The charge, and that also decreased by 1. All right, if we look at our conjugate acid, how did we get that formula? We looked at our conjugate, we looked at our base, and this time we increased the number of hydrogens by 1. All right, likewise, we also had to adjust the charge. We increased our charge by 1 as well. Okay, so I want you all to see, let's see if we can't apply this logic. I'll kind of try to keep this on the page here for a new acid-base reaction. We're going to do HClO4 and F minus. All right, I'm going to tell you that HCl4 perchloric acid is going to play the role of the acid in this reaction. The fluoride ion is going to play the role of a base. And I want you to try to predict our products based on what we just discussed. All right, we should be able to predict the product. We should have a conjugate acid and a conjugate base on our product side here. All right, so in order to get my conjugate acid, what am I going to look at? My acid or my base? The base. Okay, in order to get my formula here, I need to increase my number of hydrogens by 1. So now I have HF. And I need to increase my charge by 1. So it's going to go from having this negative charge to just being neutral. So I'm not going to write anything. In order to get the formula for my acid, or rather for my conjugate base, I need to look at my acid. Okay. I'm going to then decrease my number of hydrogens by 1 because my acid is my proton donor. So ClO4. And what else do I need to do to this? Put my charge in. I need to decrease that charge by 1. So that's negative. Okay, and these would also both be aqueous in our acid-base reaction, takes place in solution. Cool. All right, so acid-base reactions. We're going to talk a little bit more in-depthly. We'll start talking quantitatively next class period as well. All right, but just kind of to review here, this is a topic we would have discussed last semester. When talking about double displacement reactions, this was one of our categories. All right, but it turns out that this was a very outdated definition of acid-base reactions, a little bit simplified here, called the Arrhenius definition. What we did is we graduated to the Bronsted-Lowry definition, where an acid is a role that a molecule plays in a reaction when it donates a proton, and a base is a molecule that accepts that proton in that chemical reaction. All right, so acid and bases will react to form conjugate bases and conjugate acids. All right, and we can get those formulas. Our conjugate base is dependent on the formula of our conjugate acid. We decrease the number of hydrogens by 1 and decrease the charge by 1. And then our conjugate acid formula is going to be dependent on our base. We're going to increase the number of hydrogens by 1 and increase the charge by 1. And that's how we're going to predict the products of our acid-base reactions, right? This exchange of protons that's happening between the acid and the base in our chemical equation. Cool. All right. I'm going to call it there. If you want a little bit of help trying to figure out how to work your calculator, please let's try to figure that out.